All right, so 3.1 is going to cover just your basic probability. So let's start with some definitions. Probability is a measure, which is just kind of a way of saying a number in a sense, that is associated to how certain we are of outcomes of a particular experiment or activity. So if we were 100% certain, the probability would be 1, and if we were 0% certain, then the probability would be 0. But typically probabilities fall anywhere between 0 and 1. It's really rare that you'll have a 0 or 1 probability. An experiment is a planned operation carried out under controlled conditions. So this can be like flipping a coin, rolling dice, things like that. The result of an experiment is called an outcome. So that would be whether or not you got heads or tails, or whether or not, or what number you rolled. The event is any combination of outcomes. So we always use capitalized letters to represent events. So maybe the event is getting a heads, or maybe the event is rolling 3 6s in a row. And then the sample space of an experiment is just the set of all the possible outcomes. So if you roll a dice, a fair die, excuse me, then the sample space is 1, 2, 3, 4, 5, or 6. Those are all the possible things that you could roll when rolling one die. So let's go through that one more time. Probabilities can be any number between 0 and 1. So if A, your event, has probability 0, means that it cannot happen. If A, your event, has probability 1, it means it always happens. But usually we deal with numbers in between 0 and 1. So if your probability is 0.5, that's like an equally likely chance, 50-50. So 0.5 converted to a decimal is 50%. And so hopefully that's resonating with 50-50 chance. And then similarly, if event A has probability of 0.9, that means it's just 90% likely to happen. Also, we should note that the probability of it not happening would be kind of the complement of that, which is 10%. So we'll talk more about that when we go over complements. All right, so let's look at the other terms. So an experiment, so like I said, it could be rolling a fair 6-sided die, and then the outcome would be the value of any given roll. The sample space would be all the possible things that you could roll, which is 1, 2, 3, 4, 5, or 6. An event, so you have to kind of state what the event is. We use capital letters. So an example would be an event, which is defined by rolling a 4. And then the probability of that event. So this is a pretty straightforward one. The probability of rolling a 4 on a 6-sided die, and the die is fairly balanced, would just be 1 out of 6, right? Because every face value has equal likelihood of showing up. And we'll talk about that too today. All right, so probability of a single event. So equally likely means that each outcome of an experiment occurs with equal likelihood. So flipping a coin, rolling a dice. So the probability of your event is you have to figure out what are the number of favorable outcomes. So in this case, favorable outcomes means satisfying your event A. So if your event A is rolling a 4, well, then there's only one way to roll a 4, and that is to roll a 4. But if your event A is getting an even number, well, then there's 3 ways that you could do that. You could roll a 2, a 4, or a 6. So the number of favorable outcomes in that case would be 3. And then you always have to divide by the number of possible equally likely outcomes. So for the die roll, that's going to be 6. Flipping a coin, there's 2 equally likely outcomes. So let's look at this example, the probability of getting tails when flipping a coin. So here the event T would be getting a tails. So the probability of getting a tails when you flip a coin is 1/2 or 0.5. Let's look at another example. If we roll a die and we want to get an odd, like I said, there's 3 favorable outcomes, right? I can get a 1, a 5, or a 3. So that's going to give me 3 possible favorable outcomes divided by the total number of equally likely outcomes. So 3/6 or 1/2. We have more complex events as well. So maybe we want to look at two things happening. So these are and probabilities. So in this case, our experiment is still going to be just rolling a fair 6-sided die. And then the outcome is going to be the value of any given roll. And so we know our sample space is 1, 2, 3, 4, 5, or 6, because those are the things that you can roll. So we're going to let two events be in consideration. The first event is A, the event of rolling an even number, and B, the event of rolling a 4 or higher. So the and probabilities, which is given by this wedge symbol, means that the outcome must satisfy both conditions simultaneously. So for this example, the probability of A and B is the probability that the roll is even, right? That's A, and that the roll is 4 or higher, that's B. So they have to satisfy both of these things. So the possible outcomes that would satisfy both A and B is 4 or 6, right? So this kind of comes back to that, the sets and the Venn diagrams that we talked about earlier. So then the probability of A and B would just be the number of favorable outcomes, which we have 2. We're rolling a 4 or rolling a 6, divided by the number of equally likely outcomes. So I get 2/6, which is 1/3, or 0.3. So let's look at another and example. So usually in probability, the go-to experiments are pulling cards out of a deck or rolling dice. All right, or also marbles out of a bag. That's another really popular thing. So let's talk about the probability of rolling a 7 and having one die be a 2. So in this grid here, we're showing the outcomes when you roll 2 dice. So this would be like in a board game, or if you're playing craps, you would roll 2 dice simultaneously and then look at what you rolled. And typically what you do in most games is you would sum up both face values. So in this top left corner, you're rolling 1 and 1. So the sum here would be 2. In the bottom right corner, you're rolling 2 6s. So the sum here would be 12. If you roll, let's say, a 3 and a 2, your sum would be 5. So what we're looking at here is the probability that you roll a 7. So that means that the sum of the dice is 7, and that one of the die is 2, or one die is 2 of the dice that you rolled. So the probability is going to be computed by the number of ways to roll a 7 with a 2 divided by the number of ways to roll 2 dice. The other thing we're going to look at is cards. This is another very, very popular thing to look at. And we want to look at the probability of pulling a red and a queen. So this is a little bit easier to understand. We're going to look at cards that are red and are queens, so red queens, and then just divide it by the number of cards. So, all right, so how do we do this? With the dice, you want to look at all the ways to roll a 7, which are now highlighted in blue. But you also have to make sure that one die is 2. So all the rolls that have a 2 in it are highlighted in yellow. So what I'm looking for is where they intersect. So I see that they intersect here at a 5-2 and a 2-5. So it's going to be 2 divided by 36. There's 36 ways to roll 2 dice. That reduces to 1/18, and I get 0.05 repeating as my probability. As a percent, I could write that as 5.56%, right? So you just basically do the Venn diagram version of this and then count the number of elements in that set. For the red queens, I'm just looking for red queens, and there's 2 of them, and so I can reduce to 1/26. So remember that there are 52 cards in a deck. You cannot forget that all semester. And we just get the decimal approximation and convert to a percentage. So let's look at OR probabilities. So OR means that the outcomes must satisfy at least one of the stated conditions. So again, we'll kind of look at the same example here. Rolling a fair six-sided die, we know what our outcome and our sample space is. And then we're gonna still let A be the event of rolling an even number, and we're gonna also still let B be the event of rolling a 4 or higher. But before, when we had the and, it had to satisfy both A and B. It had to be higher, it had to be 4 or higher, and it had to be even. With an OR probability, it just has to be 4 or higher, or it could also be even. So there's more wiggle room here. So the probability of A or B is the probability that the roll is even or the roll is 4 or higher. So here are our possible outcomes. So I could roll a 2, which is even, so I'm good there. I could roll a 4, this satisfies both conditions, so I'm good there. I could roll a 5, that satisfies the condition of being higher than a 4. And I could roll a 6, which is again satisfying both conditions. So 2, 4, 5, and 6 are my favorable outcomes. So the probability of A or B is 4 divided by the total number of outcomes, which is 6. So reducing that, I get 2/3 or 0.6 repeating. All right, so let's do some OR examples with the same thing that we just did earlier, right? Rolling a 7, one die is 2. But now I want to use OR in between. So to compute this, I have to look at all the ways to roll a 7, which is still highlighted in blue. And then I want to look at all the ways that one die is 2. But now this is a bit tricky because to say one die is 2, I didn't say at least one die is 2, I said one die is 2. So I cannot include this double 2s because 2 die are 2 in that case. So I get rid of that guy and then I just count up all the things in my set. So I've got 2, 1, and 1, 2, 2, 3, and 3, 2, 4, 2, and 2, 4. I've got 2, 6, and 6, 2. Plus I have all the ways to roll a 7 as well. So 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, 1, 6. That's a lot. So there's actually 14 of those and you can count them out. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And reducing that to 7/18 gives me a decimal approximation of 0.389. So I would call that, or 38889, or however far long you want to round it to. So however far you want to round it to, and then you can turn it into a percentage as well. So let's do it again with the red cards and the queen. So now I want red or queen, not red and queen. So red or queen means I can be red or I can be a queen. So how many cards have I kind of identified here? I've got all the red cards, plus I've got 2 more. I've got queen of clubs and queen of spades. So that should put me at 28 cards divided by the total number of cards, which is 52, giving me 7/13. Decimal approximation, or I can write it as a percentage here as 53.85. So let's look at something really quick about this 28/52. Something interesting is happening. The probability of being red is the number of red cards divided by the total number of cards. That's 26/52. The probability of being a queen is the number of queens divided by the number of cards. So that's 4/52. And let's turn our attention back to being an and. The probability of being red and a queen is just those 2 cards, that queen of hearts and that queen of diamonds, the overlap area. So something cool happens. If I combine them in this way, so adding probability of red with probability of queen, and then subtracting the probability of the intersection, I get 28/52, which is the same probability of being red or a queen. So this is the addition rule. It's actually really neat. We're going to cover it in 3.3, but it's a really handy tool. So basically you just kind of double count the intersection and then correct. So we'll talk about that again a little bit later on. So let's talk about one more item. It's going to be complements. So we know that the complement of a set, right, is like not A. So the complement of A is just not A. So the complement of an event consists of all outcomes that are not A, right? So kind of changing it into that set notation, set theory into probability. So if I take the probability of A and I combine it with, through addition, the probability of not A, then it has to be 1. So this is the main idea in complements. Like, so let's say the probability of you getting a flat tire today is 0.01. You have a 1% chance of getting a flat tire. Then you have a 99% chance of not getting a flat tire, right? So on any single day, you're either going to get a flat tire or you're not. Those are the only two possible outcomes. Like there is no third option. So those together combined have to be 1. So that's where this idea comes from. And we actually use complements to find probabilities in a clever way, which we'll see in a little bit. So let's do the example again of rolling a 6-sided die. Let's let A be the event of rolling a 1 or a 2. So then A prime would be not A. So A prime is the event of rolling a 3, 4, 5, or 6. So the probability of A, the number of favorable outcomes, there are 2 of them. I could roll a 1 or I could roll a 2. And I divide that by the total number of outcomes, which is 6. So the probability of rolling a 1 or a 2 is 2 out of 6. The probability of A prime is rolling a 3, 4, 5, or 6. So that's going to be 4 out of 6. There's 4 ways to do this out of 6 possible outcomes. If I add up the probability of A plus the probability of A prime, I get 6 over 6, which is 1. So this always happens with complements. All right, let's do another example. Let's flipping a fair coin twice, and we want to get 2 heads, which I'm going to call HH. So A is the event of rolling 2 heads. So not A, or A prime, the ways to not roll 2 heads, I'd have to get a heads or a tails and then a heads, or then a tails, tails. So there's 4 ways to flip a coin twice. Those are heads, heads, tails, tails, or heads, tails, tails, heads. So the probability of A, I only have 1 outcome that would work, which is heads, then heads. The probability of A prime, I have 3 that work. So notice again that the probability of A plus the probability of A prime equals 4 over 4, which is 1. So again, this is always going to happen with complements. All right, so that's all she wrote for this lecture, and good luck. I will talk to you soon.